All right, continuing with 8.7, we're using the trapezoid rule. And the objective here is to not draw rectangles, but to draw trapezoids. And you can see in the pre-drawn grid that I gave you, the trapezoids are going to leave much fewer gaps or less error. So what's happening is the area of a trapezoid is 1/2 the height times the sum of the two bases. So if I divide these all equally, the height would be the delta x, the change in x, this distance right here, because the trapezoid is standing on end instead of laying down. Now, if you try to find the area of a trapezoid, if I label some of these, this would be x sub 1, this would be x sub 2, x sub 3, x sub 4, and so on. It turns out that you're going to use each one more than once. Like the first trapezoid's area would be 1/2 delta x, and then the bases would be your first one, which is whatever it is at the initial spot, x sub 0, plus x sub 1, because those are your two bases. Then you're going to add the next triangle, or the next trapezoid, and it's again going to be 1/2. Change is going to be delta x. And now you're going to take f of x sub 1 and add f of x sub 2, and you'll continue with this process. F of x sub 2 plus f of x sub 3, and all we're doing is using the trapezoid rule from basic geometry. And so you'll notice that the first term only gets used once. That x sub 0, it only shows up one time. And it'll keep going all the way out to the last term, and the last one will only get used once. That last one will be 1/2 delta x, f of n is the last one, so x n minus 1 plus f of x sub n. So this guy will only get used once. But all the other ones appear twice. F of x sub 1 appears in the first trapezoid and in the second trapezoid. F of x sub 2 appears in the second trapezoid and the third trapezoid. So what happens is, when you are adding these all up, the trapezoid rule says you're going to have your delta x, which is your b minus a over the number of trapezoids you're making. And you're going to have the 1/2 out in front. You're going to have a delta x, and then you're going to add all of these bases, which are actually the y values. You have the first one that appears once. You have 2 of the x sub 1s. You have 2 of the x sub 2s. Keep on going with 2s. You're going to have 2 of the x sub n minus 1, and then just 1 of the x sub n. So you'll add up all of those, times it by 1/2 times the delta x, and you'll have the area of all the trapezoids. So if we look at example 1, and they wrote a little different in the book, but this seems to be clearer to me when I look at it. We're at example 3 now. It wants us to apply the trapezoid rule to find the area, or the integral, from 2 to 4 of x squared dx using trapezoid's rule with n equal to 4. So we're going to have 4 trapezoids. That means that delta x is going to be 4 minus 2 over 4, or 1/2. The thickness of each one is 1/2, which means the height of each trapezoid is 1/2. And we're going to make 4 trapezoids, so my first stopping point, x sub 0, would be where I start. X sub 1 would be 2 plus 1/2. X sub 2 would be 2.5 plus another 1/2. X sub 3 would be 3.5. X sub 4 would be 4. So we have 1/2 times by, and they wrote it really strange in the book. Yeah, I'm not going to write like that. 1/2 times by the delta x, which is 1/2. And then we're going to have whatever it is at f of 2 plus 2 of f at 2.5 plus 2 at f of 3 plus 2 at f of 3.5, that's 3.5, and then 1 at f of 4. So 1/4 out here. Plug the 2 in, 2 squared is 4. Plug 2.5 in, 2.5 squared, and we have to keep on going here. 2.5 squared is 6.25. Oops, times 2. Plus 2 times 3 squared is 9. Plus 2 times 3.5 squared is 12.25. Plus 4 squared is 16. So that will give me 1/4. When I put all of that together, I got 75. And 1/4 of 75 gives me 18.75. And so that's the area under the curve, approximating it by trapezoids. Example 4 wants us to find the errors in the midpoint and trapezoid rules. And they're giving us 0 to 1, x e to the negative x dx. And they're telling me it's equal to 1 minus 2e to the negative 1. Find the absolute errors in the midpoint and the trapezoid rule approximations to the integral with n equal to 4, 8, 16, 32, 64, and 128. That's a little much as my number of rectangles or trapezoids. So we're going to say they're actually doing 16, so we'll do 16. If we do delta x is equal to 1/16, because from 0 to 1, if I have 16 rectangles, it's going to be 1/16. And then we're going to use the sigma notation on it. So if I'm doing rectangles, I'm going to sum up from k equals 1 to 16 of them. And I need to find out what f of the middle between two of them is. So one of them is k minus 1 over 16, plus the other is k over 16, any particular term, and divide it by 2, and that will give me the middle. And I plug it in, that'll give me the y value at the middle, times by 1/16, that's the width of the rectangle. Cleaning that up, we have f of, they collect their like terms, got common denominators, and worked this nonsense out with a lot of patience here. You would get 2k minus 1 all over 32. Still, your thickness of your rectangle is 1/16. If you evaluated all of that, you'd get 0.2644 and a bunch of numbers after that. If you do the same thing with the trapezoid, this was midpoint, I'll put m equals. The trapezoid, well, now we have to have 1/2 the function at 0, the starting point, plus we have to sum into it from k equals 1 to 15, we're going to have the function of k over 16. And then we're going to add to that 1/2 of the function at the last point, and the whole thing is going to get times by its thickness, and they say that you get 0.2639156, and on and on and on. So how do you find the absolute error on the midpoint? You would take the midpoint at 16 and subtract the exact answer. And when you do that, you get approximately 0.000163. For the absolute error on the trap, you do t of 16, whatever we got up there, subtract 1 minus 2 e to the negative 1. And the book says we get 0.000325. If you look at them, the error is a little less when you're talking about the trapezoid. But in the grand scheme of things, they are pretty close. We're only off by, what, 3/10, hundredths, 10 thousandths apart from each other. So the error is not that far. This concludes example 4.